higher vapor pressure than your pure PA, which means your B is more volatile. Okay, if today I give you a number, okay, PA equals to 300, PB equals to 100. Don't draw this, you should draw in opposite direction. Okay? Alright, so once you have this, okay, and you have a 1-to-1 mixture of A and B, okay? So I did not put this one here now, okay? Put it on your hangout so you don't see it. That means inside your solution, your XB, I should redraw this line because it's 50-50, right? So we know your XB is actually at 0.5. XB equals to 0.5, okay? Which is this line. This is your XB, okay, for your solution. Yes? We'll specify, we'll go to that point. Okay. So in your second line, I say at PT equals to a certain torr. You need page number?
Yes.
Number 6 or number 7? 6 or 7? Because in the update version, I add one more slide in front. So it's
Temperature dependent.
no, not one slide before the temperature dependence.
Is that the binary ideal solution? Binary ideal solution.
Yeah, after that,
I think the old version you have the same thing too. Dependence, binary system. So the new version is done. Okay. So if you have downloaded the new version, you are not going to see this slide. Okay, but in the old version you will see this. Okay, so I will just write down all the information I put on the slide. Okay. So the first questions we want to ask is actually, at what pressures the first molecule appear. Okay? So under this specific composition in your system, okay, then you can actually change your pressure, right? You can lower down your pressures, okay? And when you see the first molecule appear, that means you have liquid become vapor, right? So we know when you lower down the pressure, once you hit this line, okay, when you hit this, okay, that's where you're going to see your first gas molecule appear. Okay? So basically what this question is going to ask is actually, once you have this plot, okay, at this specific composition, what is your T external? Right? Everybody get the idea? So how do you determine T external based on your plot? So how would you do it? Okay, so the things you need to remember is actually, since this curve, okay, represent the ideal solution, right? Like we know you can write your P total as this. So you know your P total is going to equals to PA star times your XA plus your PB star times your XB. Okay? And you know your XB is equal to what? 0.5. So your XA equals to 0.5 as well. do you know your PA star is 100? What's your PB star? 280. So you know is equals to 100 times XA is 0.5 plus 280 times 0.5. And this gives you a number of 194. Okay? So, the important thing of this question is actually you need to know where you're going to see your first molecule appear. Okay? And you will know it. Another thing you need to know is actually, okay, this is where the first gas molecule is going to appear. Okay? And this is actually intersect with your P total for your ideal solution. Because it's ideal solution, then you know your P total is equal to this. Then you can calculate the P total using this equation. Once you know the mole fractions in your solution and the corresponding vector pressure of pure substance. Alright? Okay, so let's answer the first questions. Okay? Second question. At P total equals to 164. What is the XB, XBV, and NB in the liquid form versus the NB in the vapor form? Okay? So first, you see the question, okay, it's a P total equals to 164. Okay? 162 is actually between 100 and 280, right? That means it's actually, most likely you have a coexist of two phases, right? So you know this is 190, this is 100. So 160 must be somewhere in between these 2 points. So assuming this is 160, okay, it's going to intersect these two curves in two different points. Okay? So can you calculate the XB? XB is the mole fraction of B in the solution. Right? XBV is actually a mole fraction of B in the vapor phase. And this is actually, if you look at the B, how many of B's exist in the liquid form? How many exist in the vapor form? I want to know the ratio between these two. Okay? So this is what this question is asking for. Alright? So how do you handle this? Alright, so the first thing you just know is actually, previously if you have pure liquid, okay, everything is very easy, just using the ideal solution equations, right? But when you hit here, what's going to happen is actually, once you hit here, okay, you are going to form your first vapor, right? That means the composition inside your vapor form will actually equals to this guy. Alright? So if you keep decreasing your vapors, okay? For example, let's go to this point. What's going to happen is actually, this is your solution, okay? And you have 50% of A and B, okay? If you go to this specific vapor, this specific external pressure, okay, then you know your molecule start to evaporate. And you also know your B is going to evaporate faster than your A because it's more volatile. Okay, so since more molecules escaping from the solution, more B escaping from the solution, then you know your chemical composition of your B is going to decrease inside your solution, right? Therefore, your XB is going to decrease. Make sense? Okay. And at the same time, once you hit this, okay. So in this beginning, you know your first B is going to become vapor, right? That's why inside your gas phase, most of the stuff is in the XBV is actually very high. Okay? When you decrease the pressures, now not only your B can evaporate from the solution, your A is going to evaporate from the solution too. Therefore, the composition in your vapor phase, okay, in the beginning you have very high concentration of your B, okay. When you lower down your concentration, some of the A is going to evaporate into your gas phase. Therefore, it's moving to this direction, okay. So when you hit at for a given external pressures, okay, then you can describe your XB and XBV using these two curves. Got it? Or you still feel confused? If you are confused, you need to ask me now because this is critically important. Okay, I want to make sure you know how to calculate this before your final. Okay, so when we lower the P external, okay, to this point, we're going to have a first molecule evaporates, okay, and the chances are that your B most likely have evaporated a lot more than your A, okay. So these linear lines describe the XB, which is the chemical composition in your solution, okay. To describe the chemical composition in your vapor, you should follow this curve underneath. Okay, so when you hit this, when you hit here, then this is your XB inside the solution. If you want to know your chemical composition in the vapor form, that's the chemical composition. Okay, and you know because V is a lot more volatile. So if you see what's the XBV here, you will be actually larger than 0.5 in the solution, right? If you keep lower down your pressure, okay, then you know B will actually escape a lot more faster than your A. Okay, so your B is going to decrease more in the solution, right? Because a lot more B is escaping from the solution. So the more fraction of B inside your solution is going to decrease a lot more. That's why your XB moved to a lower number. Okay, so originally you have 50% is actually B in your solution. But under these pressures, okay, you have more B goes to the vapor form. So the composition, the more fraction for B decreases. If you go to here, maybe you are hitting somewhere between 0.4. Okay? The same thing happens here, okay? In the beginning you have most of it is actually B, right? But when you lower down your P external, now a lot more A can go to your gas phase too. Okay? Then this one will go down too. Okay? So once you keep lowering down, you know, these two, original is single points, right? Once you hit this line, it becomes 2 points. Because once you hit the lines, okay, at a given pressure, you are going to start to have two phases coexist. Okay? Then the more fraction of B in these two phases will change accordingly depending on your B external. Okay? But good thing is actually we know how to describe these two curves, so we can actually calculate your XB, XBV. Okay? So go back to our question, okay? Assuming today we are at these specific conditions. Okay, so from here we know you must exist in a two-phase condition. That means you should be able to calculate your XB and XBV. Okay, so how do we calculate that? Clean up this a little bit. So we want to know what's this? And what's this? Because this gives you the XB in the vector, This gives you the xp. Okay? So how do we calculate this? How do we calculate this? It is actually very simple to calculate xp, okay? So we're going to calculate xp now. In the order analogy, you need is just